Hello students, in this video we'll have third illustration of chapter 5. Four questions were given here. The first one is, what happens if a bar magnet is cut into two pieces transverse to its length or along its length? Let us address this one first. We know that in any bar magnet we have north pole and south pole. And how do we give magnetic dipole moment of this bar magnet? If length is 2L, then the magnetic dipole moment capital M is given as small m into 2L. What is small m? Pole strength, 2L is length. Now, what if I divide this bar magnet in this way? Say this is the bar magnet, and if we cut it like this, in that case we will have two pieces like this, isn't it? But each one will have length same 2L only. What difference would it make? Now when you divide this along the length, at that time you are dividing poles. So pole strength will become half, and now the new pole strength will be m by 2 m by 2. And so new dipole moment, if it is m prime, I should take it as m by 2 into 2L, and that is previous dipole moment by 2. So if you cut it like this along the length, what you are doing, you are making its dipole moment half. But what if I divide it in other way? Which is the other possible way? Other possible way is, if this is the bar magnet, you can cut it like this. And in that case, the two pieces will be of half length. Okay, so now length is not 2L, it is L. But then this part is not divided. So pole strength will remain same, and hence pole strength is L. And so if dipole moment is m double prime, pole strength is same, length is half, and then again it is m by 2. Check, dipole moment is m into 2L, previous dipole moment mu is ml, that is half. So it makes no difference you cut it along the length or cut it perpendicular to the length, dipole moment becomes half. Question here is, what if you divide a bar magnet into four pieces like this, and now if you are asked how much is the dipole moment of this one part, try to find out answer of that. For now, let us move to second one of this illustration. Second question, a magnetized needle in the uniform magnetic field experiences a torque but no net force. An iron nail near a bar magnet, however, experiences force of attraction in addition to torque. Why? This is a bit tricky question. Understand the situation. We are talking about two different situations. In first situation, we have a magnetized needle in uniform magnetic field. So first, let us produce uniform magnetic field. Say this is uniform magnetic field. Okay, and in this, let us place a magnetized needle. So let this be a needle with say north pole here, and the other one is south pole. Let it be blue. So blue is south pole, red one is north pole. Now what happens in this case is, when you say that magnetic field is from north to south and field lines are going from left to right, so left side should be north, right side should be south. And then this part of needle will experience force. How much force? Force is MB, pole strength into magnetic field. If you remember, in electrostatics, we have one force, F is equal to QE. So this is another force. F is equal to Q is force on charge, F is equal to MB is force on pole due to magnetic field. And similar force you have on south pole, but in opposite direction. So if you sum up these two, force on north pole, force on south pole of the needle, resultant force will be 0. But as the two forces are along different lines, there is some perpendicular distance and hence there is torque. So this needle will not move left, right, up, down, but it will rotate because the lines of actions of these forces are different. And hence no resultant force, but there is torque. Now look at the second condition, an iron nail near bar magnet. Now be careful here. Now we are not talking about this field. Now we are talking about magnetic field of bar magnet. Which kind of field we have when we talk about bar magnet? If this is north pole of bar magnet, then the field lines are like this. So it is not uniform field. Okay, when you are talking about bar magnet, the field is not uniform. And now in this, if you place a needle or any iron piece, what will happen? The domains of any ferromagnetic substance will start being aligned, and then the field experience here and field experience here will not be same. This needle will temporarily behave like magnet, but the magnet will have north pole here and south pole here. This nail or needle or any iron piece, whichever it may be, will become magnet with south pole close to north pole of external magnet and north pole of the induced magnet. This is induced magnet is away, and hence force on this part will be more as compared to force on the other end, and hence it is definitely experiencing torque because again the lines of action may not be same, so torque is definitely there, but then force is also non-zero, unlike this case where field is uniform, so force on north, force on south both are equal, whereas field of bar magnet is not uniform and hence the forces are not equal in magnitude, so resultant force is not zero. So that is the difference between field of bar magnet and uniform magnetic field. Let us look at third one. Must every magnetic configuration have north pole and south pole? What about field due to toroid? Very interesting question. Must every magnetic configuration have north pole and south pole? What about magnetic field due to toroid? Now, to answer this question, we must first understand the origin of magnetic field, from where magnetic field originates. Magnetic field originates from motion of charge on circular path, current carrying ring, you may say. So how come magnet is having its magnetic field? So the explanation is there are so many electrons moving in circular orbit and they have their own magnetic dipole moment. So each electronic orbit is like tiny dipole. And in case of magnet, what happens is the ferromagnetic material in which you have all these tiny magnetic dipoles aligned will have net dipole moment. Okay, and we say that instead of considering this tiny electronic current loops, we may consider a circular loop on its surface, and we say that say this is the reason behind the magnetism of this piece. Okay, so whenever you see any magnet, you should be able to understand this situation, that inside all the tiny electronic loops or atomic dipoles must be aligned, and if these atomic dipoles are not aligned, what you are talking about is paramagnetic substance, or maybe it is because of the domains which are randomly oriented. So now, when we talk about magnetic monopole, the question here is, look at the question. Must every magnetic configuration have north pole and south pole? Now, this is the basic reason for magnetism. Okay, wherever you have magnetic field, you should understand there must be this kind of situation prevailing. Okay, so how to separate this north pole with south pole? It is not possible. It is not possible to separate north and south. So that is why in high school or primary level we are told that if you divide north and south pole, if you divide any magnet, it's not that you will have one north pole and other south pole. This will not happen. What will happen? If you have a magnet and if you divide it into two parts, what you will get is two smaller magnets. Again divide them. What you will get? You will get still smaller magnets, and that process will continue as long as you keep on dividing. And if you can reach atomic level, you will see that even the atom is also having north-south pole. Okay, so magnetic monopole does not exist, and this is the reason behind that. You cannot separate north-south. And what about toroid? Very good question. What is toroid? Toroid is like, suppose if you have a solenoid and you bend it. So what is the nature of magnetic field of solenoid? Solenoid's magnetic field is like this. Okay, one of the ends behaves like north pole, other end is south pole. So suppose this is solenoid. Now if I bend it, uh, if I bend the solenoid like this, what will happen? The field lines which are coming out from this part, I am giving chance to this field lines to enter into south pole when I bend it. So field lines coming out from one pole will enter into south, and then I have closed loops produced. Okay, inside the toroid I have closed loops of magnetic field lines produced, and hence I don't have any magnetic field in this region, I don't have any magnetic field in this region, but inside I have closed magnetic field lines, and because of that I don't have any north or south pole. Okay, this is like closed magnetic circuit, so there are no north or south pole inside the toroid. Lastly, we are asked two identical looking iron bars A and B are given, one of which is definitely known to be magnetized. We don't know which one. How would one ascertain whether or not both are magnetized? If only one is magnetized, how does one ascertain which one? So basically you are given two pieces and you are asked to find out which one is magnet, which one is not. Again, a very good question. What you can do here is, suppose this is say piece A and other one is piece B. What you can do is first bring them together and see if they are attracting each other. Suppose if they are attracting each other, one of the two is magnet. That is for sure. If they don't attract, none is magnet. Now, if they attract, how do I know A is attracting B or B is attracting A? The answer is, uh, see which part is being attracted. Like if I suppose if I see that A is being attracted to ends, suppose if I place A near the middle part of B and if it shifts to end, then I should understand that B is having magnetism in this region. Okay, for any magnet the maximum magnetic field is near poles. So check middle part. The one who is not having magnetism in middle part, or the one where attraction is not experienced in middle part, is magnetized piece, other one is not. Okay, so that is how you can find out which one is magnetized. So that is all about illustration 5.3. I hope you could understood. Thank you.